I want to talk to you about a particular class of problems, probably the hardest force problems, and these are called inclined plane problems. So inclined here just means tilted at some angle. Plane means, something mathematically flat. So this is problems with flat surfaces at an angle, or in other words, what we might call them in everyday life is like ramps, right? So if we have an object on some tilted surface, how do we look at that? So here's our little picture of what one might look like, right? So we have some surface that is tilted, and we have some object on that surface, a box or a little toy car or whatever. So it turns out there's a particular mathematical way to attack these that is different than other force problems and other problems in this class. And here, let me point some things out. So if we look at the forces on this block, we know that there is going to be at least gravity on it and a normal force on it, right? The normal force we know is going to be perpendicular away from the ramp. So it's going to be in like this direction. And we know the normal force is as big as it needs to be to keep the acceleration perpendicular to the ramp 0, right? So the normal force keeps A equals to 0 in the direction perpendicular to the ramp. Now is another good time to review our perpendicular and parallel symbols from geometry class. We're going to use these a lot in inclined plane problems, a little bit in some other problems, but definitely a lot in inclined plane problems. So pause this and memorize these, and let's continue. Okay. So we know a few other things. So we know that our normal force is in the perpendicular direction, meaning it is perpendicular away from the surface. This is at 90 degrees. This force vector is at 90 degrees to however our surface is tilted. We also know that if we have friction, we may not have friction, but if we do have friction, that is lowercase f friction, it would be in some direction parallel to the ramp, right? Because the direction of friction is always parallel to the surface. So, maybe up the ramp, maybe down the ramp, it depends on context. The last thing we know is if there is an acceleration, because the perpendicular acceleration is 0, the direction of the acceleration, if it existed, would also be up or down the ramp. In other words, the direction of our acceleration would also be parallel. Okay, so we're seeing a lot of things that are parallel and perpendicular. We're not seeing a lot of things in the x and y directions as we normally define them, right? This is x and this is y, and pretty much none of these are lined up with either the x or the y very nicely. Okay, so what this means is it's going to be very convenient to define a new coordinate system for inclined planes. This is one of the few times in this class that we'll do this. It might be the only time in Physics 106, actually. In physics in general, there are very many examples of using a different coordinate system that makes solving a problem much, much easier. This is the biggest one in Physics 106. So the physics is all the same. All we're doing is like labeling our directions differently, and it makes things way, way easier. So as you probably could have guessed, this new coordinate system is going to have one direction perpendicular to the surface and one direction parallel to the surface. So if we draw those axes like this, they look something like this. Different books label them different ways. I am going to label them the way I prefer, which is labeling them this as the perpendicular direction, this as the parallel direction. Some books choose to instead keep the labels X and Y, but rotate what they call Y and what way they call X. I find that confusing. I like just using these new labels for the new directions, because then we can still use X and Y, if we have to. Okay, so as a result of this new coordinate system, now normal force and friction are lined up with this really nicely. And as a result, they're much easier to deal with because they're purely in the perpendicular or parallel direction. All perpendicular or parallel, no other components to deal with. So this is a good thing. The bad thing, the one downside of this, is that gravity now, which we mentioned but didn't go into, gravity is pointing straight down, which is not in the purely perpendicular or purely parallel direction. So gravity gets split into two components. But it turns out the benefit we get from making these easier to deal with is way bigger than the downside of this. And this is actually made even easier by the fact that we usually know the mass of the object, and we usually know what this angle is, and you'll see if we know those two, we can basically write down the X and Y components, the parallel and perpendicular components of FG, and then those are forces that we know and can use in the rest of the problem. All right, so let's draw kind of a conceptual picture of what this new coordinate system is going to do. So let's take this same image. So we have our block on a ramp. I'm going to get rid of this force just so it's a little cleaner. We have our block on a ramp. Let's say there's no friction, or we're not going to worry about friction right now. Let's just stick with the basics here. So if we draw a free body diagram of this, we know we're going to have gravity in the straight down direction, and we're going to have the normal force perpendicular to the surface. So that's going to look something like this. And we want to figure out how big these are. Now remember, the normal force can be, as big or as small as it needs to be to keep the acceleration in this direction 0. So that is A perpendicular equals 0. That is what the normal force is doing here, keeping the block from falling through the ramp. And in this case, Newton's second law, as we learned it, the sum of the forces equals the mass times the acceleration. This is the vector version of this equation. And remember, we can split this equation into like the x and y directions, so we get one equation for each. It turns out there's nothing special about doing that with the x and y equations. You can do this in any direction, and it's true, which means that we can also split this into a direction in the perpendicular equals ma perpendicular, and also the parallel. So this is huge, because right away we have a perpendicular equal to 0. So that means the sum of the forces in the perpendicular direction has to be equal to 0. We'll be back to the parallel in just a second. So what forces do we have in the perpendicular direction? Well, let's draw our perpendicular axis on our picture. So our perpendicular axis is in the same direction as this normal force, right? And it's also, if we continue the axis back on the other side, it looks something like that. So our gravity does have a component in this perpendicular direction. So lots of students want to, I'm going to draw this in red, this is what you should not do. They want to draw a line like this to figure out the components. And that is wrong. That is wrong. So what we want to do is we want to think about this gravity as the hypotenuse, and draw two sides that are perpendicular to each other that add up to this gravity. So in other words, we want two vectors along these two directions. So note this direction, I haven't drawn my angles quite the same here, but this is supposed to be the parallel direction there. And now you can see I have a triangle. The force of gravity is the hypotenuse, and we can split it into a component along this direction and a component along this direction. If it is helpful, I can redraw this rotated a little bit backwards. So in other words, if we rotate things so our surface is flat, maybe I'll put it like this. We rotate our heads to look at this so it looks like the surface is flat. We end up with something like this. So we have our block like this, but gravity is not pulling straight down anymore. It's pulling at an angle, right? So our free body diagram is going to look like the normal force straight up, and gravity is like that. And now all we're doing with this gravity is figuring out these two components that are perpendicular to each other, just like we would X and Y components, right? But now these pictures just rotated. Okay, anyway, if that's helpful, great. If that doesn't make sense, that's okay. This doesn't affect anything. Okay, takeaway. We want to find these two components of gravity. Now, if we're going to do that, we need to know what this angle is. In most problems, the angle is something you are given. It certainly is possible to write a problem where the angle is the thing you are trying to find. And you may encounter that, but in 90% of problems, you're given the angle of the ramp. So we'll just say this is angle theta. We'll keep that general. It turns out you can do some geometry to convince yourself this is true. If this angle is theta, the tilt of the ramp, then this angle is also theta. You can have a good geometry argument why this is. The way I think of it is this. If you imagine this ramp starts flat and you rotate it clockwise by angle theta, well, when it's flat, your normal vector is straight up. And if you rotate the surface by theta, you're also rotating the normal vector by theta. And so that's telling you that this angle is theta. And if you have, opposite angles where lines cross, those are the same angle. So anyway, that's one way you can see that that's true. But you can also just start with that. That's fine with me. You don't need to do a geometry proof every problem. Okay, so this component is FG parallel. This component is FG perpendicular. I want to see how big those are. So let's say I know the hypotenuse, I know theta, and I want these components. So that is pretty straightforward. FG perpendicular is adjacent to theta, so that's FG times the cosine of theta. FG parallel is opposite, so that is going to be FG times the sine of theta. And if we know theta and we know the force of gravity, that's it. We will get some numbers for FG perpendicular and FG parallel. Now, these two forces are important because they're affecting lots of other stuff in the problem. So let's go back to our Newton's second law, acceleration equals 0 in the perpendicular direction business here. So in the perpendicular direction, we have normal force up and this perpendicular force of gravity down and to the left, right? So this is normal force minus FG perpendicular is equal to 0. That's where, we're adding up the forces and these are in opposite directions. Their perpendicular components are in opposite directions. So this means that our normal force is the same size as our perpendicular force of gravity. So in doing this, in most problems like this, we can figure out how big the normal force is by looking at this other force that it has to balance out. Yes. In the parallel direction, in this case, there is only one force, right? The normal force is all in the perpendicular direction, so the only force in the parallel is FG parallel. So if we sum up all the parallel forces, we get just FG parallel, and the sum of the forces is equal to MA, so this is MA parallel, the acceleration in the parallel direction. So this gives us the acceleration, right? We know what FG parallel is. So if we knew the mass, we could solve for the acceleration and find out how fast the block is accelerating down the ramp. So without any numbers, I just wanted you guys to kind of see how these problems get set up. Next, we're going to do an example like this with numbers, but I think it's useful to see it all kind of conceptually first. These results are mostly usable in other problems. There are some things that can change, right? So if we had friction, that would change this equation and this would not be true anymore. These would still be true as long as our angle looks like that, but there might be other pieces to consider in the parallel direction. In the perpendicular direction, this is always going to be true unless there is some other force pushing on the block up or down, like if there's a rope tied to the block or something like that. So this is almost always going to be true, but we could design a problem where there's an exception. All right. So lastly, I want to show you one cool result for this problem, and that is FG parallel is equal to MA, right? So FG sine theta is equal to MA parallel. And our force of gravity, we never even addressed this, our force of gravity is equal to M times G, right? So this is mg sine theta, which is equal to MA parallel. Now this mass is the mass of the object. This mass is also the mass of the object, right? That's, the force is how hard you're pushing on the object to get it to accelerate. So these masses cancel, and we're left with the following. A parallel is equal to G sine theta. So as long as there is no friction and no other forces on this block, if we have a block on a frictionless ramp, it is going to accelerate down the ramp at a rate given by G sine theta. So we can do a couple quick checks here. If theta equals 0, if our ramp is completely flat, sine of 0 is 0 times G still gives us 0, so that A parallel is 0. So if we have a block sitting flat on a ramp, it is not going to accelerate down the ramp because of gravity, because the ramp is flat. Okay, that makes sense. So that's good. We could also check what happens if our ramp is tilted up all the way 90 degrees. So if our ramp is tilted up, all the way like this, that's 90 degrees, sine of 90 is 1, and our acceleration is just equal to G. So in other words, if you're on a ramp like this straight up and down, you are just falling straight down as if there was no ramp there. So this is an equation that you can use in these sorts of problems. Like, I'm okay with you solving the problem by saying, oh, I know this is true for frictionless ramps or whatever, but you better be sure it's a frictionless ramp and there's nothing else pushing on the block, because otherwise you might get the problem very wrong.